All right, hello and welcome. So today I'm doing a video on limiting excess and percent yield in terms of stoichiometry. So I'm going to super quickly just define what this stuff is, but it's kind of self-explanatory, and then I'm just going to get into a practice. So let's start off with limiting and excess. So with limiting and excess, it's kind of self-explanatory, but limiting is whatever reactant runs out first, and excess is whatever reactant you have left over. So a quick example that you see probably every day is, let's say you go to the store and you buy some hot dogs. Oh, that's way blobbier than I wanted. You buy some hot dogs. 1, 2, 3, 4, 5, 6. You get your hot dogs and they come in a nice little pack of 6 hot dogs. But you want buns too. So you go to the store and you get some buns. And buns are a little different. They come in packs of 1, 2, 3, 4. Unfortunately, you know what? Let's make it more realistic. They come in packs of 8. So you have your 8 buns. When you're making hot dogs, one of these is your limiting and the other is your excess. And while you're limiting, it's going to be your hot dogs. And your buns will be your excess because you have 2 more buns than you need. So even though you go ahead and make 6 wonderful hot dogs, pretty much done with this example. Even though you make 6 wonderful hot dogs, you still have left over 2 buns. So this is kind of how it works in science. When we react to things, it's hard to react them in the perfect ratio. It really is, especially when you get down to atoms. And what ends up happening is you have some left over. And it's very valuable to scientists to be able to predict this and calculate it and be exact. So with that said, that's limiting and excess, and I'll show you how to do it in just a moment. Next, we have this last part, percent yield. And this basically accounts for human error. Basically, in a lab, you might do some reaction and you get 47 grams of product after doing lab stuff. I don't know, you've got your little, whoops. You have your little flask with your liquid in it, blah, and it's 47 grams of product. But the problem is your math said you should get 50 grams. So, oh no, you have 3 grams less. Well, that's where percent yield comes in. It just kind of says, well, hey, we know we're not perfect, so let's figure out how close we got. And percent yield really is just kind of an algebraic equation. Whoops, percent yield is equal to the actual amount over the calculated amount and then all of that times 100, because it's a percent, we want it to be a percent. So really quickly, we can do the math for this one. Our percent yield is equal to 47 over 50 times 100, which turns out to be about 94%, which is a pretty good percent yield. So we said we produced our amount with about a 94% yield. It means we didn't get exactly what we wanted, but we got about 94% what we calculated we should have got. And that's all percent yield is. So with these definitions, let's just jump right into an example. So I have one right here ready for us. So ethane combusts with oxygen. If we were to start with 40 grams of each reactant, how much of each reactant and product will be left over or produced at the end of the reaction? Well, there's a couple of things I want to do. Number one, I want to write the balance equation. Then number two, I want to find the limiting reactant. Number three, I want to convert the limiting reactant to every other part of the equation. So I'm going to go through each one step by step, but let's start with number one. Writing the balance equation. So it told us ethane was C2H6 plus oxygen, and oxygen is O2 because it's diatomic, and it told us it was combustion, which means we're going to have H2O plus CO2. Now, I'm not going to take too long balancing this, but I can pretty much see that I'm going to need 6 hydrogens, which normally means I would put a 3 right here, but the problem is that would apply to the oxygen, giving me 3 oxygen plus 2 oxygen, which is 5, which is kind of awkward because 2 doesn't go into 5 very well. So I'm just going to scrap that and automatically start by doubling this, meaning I now have 12 hydrogens, so I'll put a 6 right there. And I have 4 carbons, so I'll put a 4 right there. And then 6 times 1 is 6 plus 4 times 2, which is 8. It's going to be equal to 14 oxygen. So I'll put a 7 right there to just go ahead and balance that out. So here's my balanced chemical equation. 2 ethane plus 7 oxygen reacts to form 6 water and 4 carbon dioxide. So with that, number 1 is done. All right, number 2, finding the limiting reactant. Well, I haven't taught you that yet, so it's a little hard, but here's the trick to finding the limiting reactant. You convert each reactant to the same product. So what that means right here is we'll take 40 grams of ethane because we have 40 grams of each right there. And we'll convert that to mole H2O. But we'll do the same thing with 40 grams of oxygen and also convert that to mole H2O. So we're going to do that first. That is the first part of finding a limiting reactant. We need to convert them to the same product. So these are pretty similar equations, 40 grams C2H6. And if we're going to go to moles, we have to convert grams to moles. So 1 mole of C2H6 over the atomic mass. This is going to be 12 times 2 plus 6. That's 24. It's about 30 grams C2H6. And then we're going to convert mole of, we're going to convert mole C2H6 to mole H2O. And then remember, when you're converting mole to mole, it's not actually the 1 mole to 1 mole. We now have to use the coefficients, so 2 and 7. All right, so what I'm going to do here is I'm going to go ahead and just check to make sure my units cancel. Grams cancels with grams, mole with mole. And so my grand total for this is going to be, just one moment while I do some math. This will be about 4.67 mole H2O. So we're going to do the same thing, but now with O2. So 40 grams O2, which that's just going to be 16 times 2. 1 mole O2 on the top. On top, on the bottom, we're going to have 32 grams of O2. And so we're going to multiply that by pretty much the same thing. We have mole O2 on the bottom, and we have mole H2O on top. And our coefficients are going to be 7 and 6. And I just realized I made a mistake up here at the top. Don't at me. So that's going to be 6 mole. So give me just a moment to fix the math and calculate the other one as well. Thank you for catching me. So my new number being 4 mole of H2O when using ethane, and let's keep the colors consistent, 1.1-ish mole H2O when using oxygen. So whatever is limiting, so whatever produces less is limiting. And this kind of makes sense. If we go back to our hot dog examples up here, if I look at 6 hot dogs and 8 buns, we already know the hot dogs are limiting because you can make less hot dogs. But now once we add in stoichiometry, it's pretty much the same thing. Whatever makes less, that's our limiting. So from this point forward, you can honestly just take a red pen and cross out excess. We don't need to care about it at all. We just know that O2 is limiting and ethane is excess. All right, so that's that. Now, step 3. I want to convert the limiting reactant to every other part of the equation. So step 3 is honestly the longest and most arduous process here. We're going to convert O2 to ethane. Whoops. Gram ethane. We're going to convert O2 to gram H2O and O2 to gram CO2. And I'm actually going to show you a shortcut on this last one, but it still works regardless of which way you do it. So let's get started. And I'm actually going to start right here with this guy. I'll just label him A because we've already done most of it. For A, we know that 40 grams O2 equals 1.1 mole H2O. So I'm just going to go 1.1 mole H2O and convert 1 mole H2O into 18 grams H2O using the atomic mass, H being 2. We have 2 of those and O being 16. And so that's just going to be 1.9, or sorry, not 1.9, 19 grams H2O. And so water is done. That's how much water we're going to get out of this. Then let's go ahead and B, and we'll do O2 to ethane. So 40 grams of O2. And we're going to do that whole beginning thing where we go grams to moles. So that's going to be 32 grams O2, 1 mole O2, mole O2 to mole ethane. And the coefficient for ethane being 2 and O2 being 7. 2 and 7. And then we're going to go back to grams of ethane. We are going to go to 1 mole C2H6 to 30-ish grams C2H6. And so let me do some math real quick. And so that equals about 10.7 grams C2H6. All right, let's finally go to the last thing. We're going to go O2 to CO2. And guess what? It's actually going to be pretty much exactly what we just did, because these all start the same until we get to the mole to mole step. this one right here, the bottom's going to be the same, 7 mole O2, but now we're going to mole CO2. And so I need to change the coefficient up to a 4. That'll be 4. And then here we just got to use the mass of CO2, mole CO2, to 44 grams of CO2. I think that math is correct. So give me just a minute to figure this one out. And this one's going to be equal to 31.4 grams CO2. All right, so that's everything. When we look at this equation, we're going to have 0 grams of oxygen remaining. We're going to have we're going to produce, oh, sorry, my bad. Let me start this one right back over. So if we look at what's left, we started with 40 grams of oxygen and we used all 40 because it's limiting. So we have 0 grams O2 remaining. We started with 40 grams of ethane, but right up here, we have to use 10.7 grams. So that's going to be 40 minus 10.7 grams. So that's going to be about 29.3 grams ethane remaining. And what we might actually call this, instead of remaining, we might say excess. We have an excess of 29.3 grams. Then we are left with 19 grams of water, 19 grams H2O, and 31.4 grams CO2. Really quickly, I said I'd give you one final shortcut, that final shortcut for this one. Well, due to conservation of mass, what we put in is exactly the same as what we get out at the end. If we put in 40 grams and 10.7 grams of reactants, that needs to be the same as the mass of products, which was 19 grams of water plus 31.4 grams CO2, which these get pretty close, I think. Let me do that math real quick. So these get pretty close. It's 50.7 equals about 50.4, which again, we're going to lose some when we do some significant figures. I took some shortcuts. For example, hydrogen weighs 1.01, but I've been using 1. Carbon also weighs 12.01, but I've been just using 12. So my shortcuts kind of get in the way here, where I'm off by about 0.3. Regardless, if I only find one of these two, I can just say I have 50.7 grams reactants, which is going to be equal to 19 grams of H2O plus some amount X grams of CO2. Well, it turns out I can probably just do a little bit of cheeky math and just subtract 19 from each side. And I should get somewhere in the range of X being equal to about 31.7 grams CO2, which is pretty close to what we calculated of 31.4. So with that said and done, that's limiting in excess. The final thing I'll say, geez, this is a long video with percent yield. If I know that my percent yield is, if I do this in the lab and it turns out I make only 30 grams CO2, then my percent yield will just be 30 over 31.7 times 100. And this will be about 94.6%, 94.6% yield. And that's all I have to say about that. Anyways, have a great day, and I'll post these notes right here in the description below. Bye.